Welcome to another episode of Code for Thought. I hope the previous episode on the Julia programming language gave you a rough overview of the language and the community supporting it. We touched on a few points Julia is said to do very well, for instance, multiple dispatch and solving the two-language problem. In the second and final episode on the language, I will be talking to two engineers, Jarvis Frost and Lyndon, on how they use Julia in concrete projects, and we'll be discussing some methods and techniques in more depth, so this is going to be a rather technical episode. I would encourage you to look up the links, including links to code repositories provided in the episode metadata. That is, if you want to find out more. So here first is my conversation with Jarvis.
I'm Jarvis Frost. I'm a Royal Society University Research Fellow in the Physics Department at Imperial College, London. My background's physics, that was what my undergraduate degree was in. And then my PhD was sort of kind of in computational solid-state physics, I guess I'd describe it as. And I've really sort of kept that sort of computational part of my research sort of going forwards into an independent academic career.
How exactly did you get into Julia programming?
So I'm a physicist, and I guess we have this sort of obsession with speed, and that's often because when we're doing computational physics, like we're really up against the limits of what we can do with the hardware that's available today. So the solution of the physical equations that govern the universe are quite tough. Computation is very unusual to have something that that scales sort of easier than n to the power of 3 in physics. And so, if you can do more computation, if you can do more flops, you can do more physics, and you can, write a better paper and sort of look at a different regime that's closer to physical reality. So we're obsessed with speed, basically, and that means that we come up against the sort of so-called two-language problem quite regularly. Physics is quite abstract. It'd be very nice to write in sort of quite a high level, very sort of mathematically descriptive language. But then we really need to sort of push the calculations through. And so before I discovered Julia, which was in about sort of 2013 or thereabouts, I'd sort of adopted what I guess is sort of more or less standard across physics currently, is that we sort of do our sort of high-level initial implementations in something like Python or MATLAB or Mathematica. And then once you finish sort of playing with your toy examples on your desktop and you want to actually move into production, you need to refactor at least some part of it in C or Fortran. And that's very slow and inefficient. When I sort of tripped across Julia, it was really being sold as sort of the solution or a possible solution to this two-language problem. So it was a language that was very expressive and it's full of very nice abstractions, which happened to be very close to what we use in physics anyway. But then it had this possibility of actually writing very, very high-performance code. So that was really sort of the thing that sort of drew me in. The initial projects I used it on were just sort of like small little new research projects, because of course it's difficult to transfer over your existing code bases. And I was just very impressed, and I actually just found it, fundamentally really joyful to write Julia.
But what's so enjoyable about it?
So because you're sort of obsessed with speed in physics, you often need to sort of look at the problem at all different levels within the sort of computer, potentially all the way down to sort of actually seeing, what is the output assembly. It's a very small subset of computer science, but we're really quite interested in going into some of the depths of what's going on a computer. And to do that with sort of traditional workflows, there's all these sort of like, fire breaks. So, if you're writing in Python, then you often use a fairly standard package called NumPy, and that's actually implemented in C, and it's actually just using, float 64s. When you're trying to figure out why your bit of Python, has numerical instability or something in it, you can find the NumPy documentation that will tell you something, but you really want to actually sometimes just see the code and actually understand what's going on. And finding that can be quite challenging. And so that's, it's a massive conceptual burden and a sort of hump to get across. And the difference with Julia is the whole thing really is Julia, and Julia has very strong introspection tools. And so, you can write your Julia function, you can run it with some arguments, and then you can just ask the REPL, just sort of where you're programming anyway, sort of what is the assembly that's being produced, what is actually happening on the computer. And that's extremely powerful when you're actually trying to understand, why is my code not going really quickly, or, can my code go any faster?
Thanks very much for the overview. So I think we can come now to a showcase, if you like, where I'm asking you to present maybe a project that you've done in Julia that you would like to highlight. Is there anything that you can talk about?
Yeah, absolutely. The first thing I would say, though, is that one of the really nice sort of emergent properties of Julia, which has been really noticeable over the last few years, is that it's possible to actually do really small projects. which sounds like quite a trivial thing to say, but what I mean is that you can develop really quickly in Julia, so you can do a lot quite easily. The language itself, due to sort of some of the specific design parts of it, so that the way that the type system is very powerful and we have multiple dispatch, it's very easy to reuse other people's code. And this, of course, is the holy grail of all programming languages, that you can have code reuse. But it really seems to be working in Julia. And so actually some of the sort of biggest joy that I've found is actually sort of lots of little projects or things that just sort of stitch together other bits, other people's code to sort of just do something useful, useful enough to actually be able to write a paper. And then you're sort of done. But the specific project that I thought I'd talk about is a little Julia package called Polaron Mobility. And so this is an implementation of some physics from the 50s and 60s. And so what we have in physics, in theoretical physics, is we have this enormous backlog, basically, of really good work that was done, by very clever people in the last sort of, 70 odd years. In particular, if we look at sort of the methods that made it and that are actually being, run on calculations on supercomputers, it's a bit suspicious that the things that we do calculations with tend to be things that are actually fairly easy to write in Fortran or C. So I think we've got this sort of, the stuff that survived and that we use tends to be stuff that is built around sort of building matrices and then firing up linear algebra subroutines, sort of fundamentally. And so this package uses a sort of a different construction of quantum mechanics called the path integral form of quantum mechanics, and it's not built around just setting up matrices. It's a little bit more sort of mathematically abstract, and that's something that was quite nice and easy to implement in Julia. And so what I practically needed to do with this package was, there were all these sort of papers from the 50s and 60s full of maths. I needed to make an implementation. And one of the really nice things about Julia is that you can almost have a sort of one-to-one mapping between the sort of the maths in the paper and how it looks in the computer code. And so the actual problem is sort of setting up these mathematical objects and then sort of optimizing them. And there I used a sort of a technique called automatic differentiation. And so this is the problem's what's known as a variational problem in physics. So we have a sort of a toy system, and you can sort of tweak the parameters, and that if you get a sort of a closer fit to the reference, then you've got a better sort of physical model. But the problem is, if you want to sort of tweak parameters, you don't know which direction to start tweaking them in. But by using automatic differentiation, you can take these sort of very complicated mathematical expressions that have sort of numerical integration in them and sort of hyperbolic functions and so on, and by sort of basically applying the chain rule, so breaking down the sort of your computer code that this has been expressed as into sort of its arithmetic operations and applying the chain rule, you can get a gradient that back propagates, and that means you have sort of much more powerful optimization methods once you have gradients. But what this package allows you to do is you can go from sort of a calculation done, with Fortran, one of these large Fortran packages that solves the electronic structure problem for a sort of an arbitrary material, and then you can predict this sort of very phenomenological quantity of its mobility. So you can predict how good a semiconductor would be for an application entirely within the computer. And so that's sort of this additional sort of useful, very practically useful thing to do when you're sort of, making new materials for, solar cells or sort of lasers or even potentially computer chips. Without Julia, I don't think I would have been able to do it so quickly and so easily, and therefore it might just not have happened.
That's quite impressive, because I think that it might be quite daunting to other people when they read a physics paper, even if you're conversant with the math, to actually translate it into code.
Yeah, absolutely.
And are there any particular techniques or features of Julia that you did use that you could highlight?
Well, the automatic differentiation is a very important one, and that really has sort of very high-level features. So because of the way the language is constructed, it's I think the technical term is like homo-iconic or something. So essentially the abstract syntax tree, so the actual sort of representation of the computer code, is actually just another Julia data structure. And so it means it's very easy in Julia to write code that acts on code, and that's a sort of a level of computer science that is mostly above me, but it means that sort of the automatic differentiation in Julia is very generic, and you can apply it to almost any function. So and again, this is one of the reasons why Julia is very powerful, and that you can reuse other people's code in a way that they didn't imagine. Whereas if I was writing in sort of a sort of more standard automatic differentiation package in Python or something, you would find there was only quite a small subset of the language which was actually automatically differentiable. So that was definitely very powerful and very, very useful. And it really, I remember implementing this and just being shocked. Well, A, that it worked, and B, that it was just a couple of minutes. And it's like, oh, wow, I've got gradients. Now this optimization is working. And the other one, I guess, is just the ability to create abstractions in Julia. So I really find that the way that I program Julia is quite similar to the way that I think and reason as a physicist. So you have very rich types, and so you can make your own types, and they operate just as quickly as just using the built-in float 64 or whatever. You often find that you can think of a natural way to build sort of a data structure which sort of describes a physical problem, and then you can supplement functions to enable you to operate on them. In Julia, because of the multiple dispatch, if the code is written generically, you usually only have to write sort of a few small bits of codes describing methods of how to manipulate your data structures, and then you can sort of use this with sort of the standard sort of library of different functions.
I think so. You mentioned three things that I find quite interesting. So there's abstraction, automatic differentiation, and then multiple dispatch. Would you say that these are the kind of key tools that you used and the advantages of Julia in your code?
Yeah, absolutely. And I think, a lot of these are sort of enabling technologies. And the thing with Julia is that, you can sort of combine stuff together. I guess the other sort of area which wasn't particularly used in this project, but is generally very useful for physics, is the way in which you can wrap around other languages with Julia. And so that's extremely important, of course. I mean, it's kind of basically sort of going back and saying that, yeah, okay, the two-language problem is a problem, but also there's an awful lot of code out there which we'd really like to use. And so it's very, very easy. I mean, it's almost trivial in Julia to call Python packages directly from Julia. And calling sort of C and C++ is not too difficult either.
The standard and traditional programming languages usually come with a rich set of development tools and debugging tools and deployment tools and a whole rich ecosystem of tools and applications. They actually add to the effectiveness and the efficiency in programming a lot. So what's it like for Julia then?
Development tools are fantastic, I would say. So there's an extremely powerful package manager, which is an enabling technology, which means that you can, when you pull in a package and you see that it's sort of solving, interdependencies from several hundred packages on the back end, and it all actually works. That's really quite amazing. And also sort of within, again, the development tools within the language, the introspection tools I find are absolutely fantastic. I mean, they tend to be more built around a sort of, a Lispy coding at the REPL background, but I don't actually mind that. I find it's quite, I've never been a particularly big fan of IDEs. There are increasing supports for IDEs, in particular VS Code I do use sometimes, and that's very nice. Because it's an Electron app, the different plugins for different languages can do an awful lot in terms of the GUI, and again do it quite so quickly and easily. So that side of things I think is kind of fine. I mean, I've never particularly felt like I needed to use a debugger in Julia. And the main sort of requirement I have in terms of the introspection is actually benchmarking the code and understanding what's going on in terms of memory allocation and what the types are turning into. And all of that I find, is very well supplied in Julia. I mean, one thing that's definitely kind of missing in Julia, or at least it feels so currently, is I've never particularly needed to run my Julia programs on supercomputers, but I definitely see that as being something that I would like to do, and certainly as these more sort of heavy lifting packages are implemented would be very useful. And there I think that's a little bit lacking. Like, the Julia language will basically, or at least on Unix, usually sort of lives in your home directory, and it pulls in like tens of thousands of files, and it's just a very long way away from the sort of a typical Fortran or C program where you can just compile it down to one statically linked executable that, okay, it might be 50 megabytes in size or whatever, but that doesn't matter. That's somewhere where I really hope there'll be sort of more development and sort of an obvious destination. I mean, I know people have used Julia on supercomputers and used it with very large jobs, but that it doesn't feel to me like necessarily the toolkit and the tool chain is there with this is the way. If you want to run your calculation on tens of thousands of jobs, you need to do this.
Finally, the code that you mentioned, the project that you mentioned that we just discussed, is it available for people to look at?
Yeah, it's all on GitHub. So I think it's still on my personal GitHub. So just Jarvis and Polaron Mobility.jl. I guess this is another thing that's very nice about Julia, and this is more sort of a a community thing. So the community is very welcoming and very friendly. And it's also very open. So, like the package manager, defaults to using GitHub as a backend. And because everyone's code is on GitHub and being sort of developed in quite a sort of modern way, I think sort of even newcomers to the language quite quickly sort of pick that up. And I think that's great for science because, unfortunately, sort of the tradition for sort of C and Fortran programs is that, they often never leave the research group. Not irregularly come across PhD students who have sort of, asked a bit about sort of more sort of research software engineering-y stuff. And then I sort of, gone to go and look at their code that potentially been working on, for several years of their PhD. And you find it's, it's just like one Fortran file, sort of 10,000 lines. And it's like, oh, can you reproduce your results from your first year? And it's like, oh, no, I commented out all of that code, but then I changed this function. It's just, these sort of the fact that sort of almost all the code is sort of open source is a really good aspect of the Julia language.
What's next in Julia for you? So are you planning any further projects?
Everything that my research group is doing is basically implemented in Julia.
My next guest is Lyndon White. Like Jarvis, he wrote a lot of code in Julia, and some of his projects are available on GitHub. We'll be discussing some of them in the following conversation.
I'm Lyndon White. I'm a research software engineer at InveniaLabs. We do things to do with improving the efficiency of the electricity grid using machine learning. I'm from Australia. I have a PhD in machine learning and natural language processing. Mostly these days, I'm interested in building software tooling to do automatic differentiation, and I write a lot of Julia code.
So before we go into your projects and the work that you've done in Julia, there are quite a number of projects that we can dive into. Let's hear from you what you think the strengths of Julia are.
So I guess to start with, the strength of almost any programming language is in its community. So I would describe Julia as having the ideal collegiate environment, just like this giant meeting pot of minds where I can say to someone, how does this complicated linear algebra thing work? And someone will be like, oh, actually, it's this thing. Or, I don't know, some people have been asking about coronavirus, and someone in the group has researched some virology and can explain, like, antibodies. So you've just got this giant collection of people with the majority of the community is either doing or has completed a PhD, probably the vast majority, 80%. It's a very academic cohort, I guess you'd say. Julia community is just incredibly helpful. As a language, a lot of the strength is in its composability, which is I think we'll talk about a little bit today. Well, I remember I once in my undergrad did a unit where we spoke to someone from industry and got real advice. And we said to him, tell me about code reuse. And he said, actually, no one reuses code. Not really. Some projects you can reuse them, but really you actually copy and paste because you have to adjust every project to meet the needs of what you're currently doing now. I think he probably overstated a little bit, but it's true that quite often code you want to reuse, actually it's not quite right and you need to edit it. And since working open source, you can edit it. But it's not really, it doesn't feel right. It's not what I was promised from reusability. Whereas in Julia, it's a lot more like the promise. It's far easier to go and just reuse and build upon someone else's package. So the composability is probably the number one big thing. Other smaller things, stuff like having the best parts of the syntax for representing mass. So the code kind of at a first look looks a little like MATLAB than it does like Python. You see square brackets and array expressions, and you use star to indicate multiply, not np dot transpose, which is just really nice. But unlike other languages which are kind of highly domain specific, you're not then put into a little box where it's like, oh, but I need to do some string processing. And then you find that string processing is incredibly difficult because it is more like a general purpose language. It does have string processing. It does have data structures.
So you mentioned quite a number of things now. I think one of them is also multiple dispatch. I guess that most listeners will be familiar with that, but could you just recap quickly what we mean by multiple dispatch, really?
Imagine I'm writing some C code. Now, if you've learnt C, the thing they tell you is a function is given by the function name and the types of the arguments. We call that the signature. So if in C, I wrote a function and I called it multiply, And I said it is multiply and it is an integer for the first argument, an integer for the second argument. That's a function. If I then wrote another function, multiply, and it's a float for the first argument, a float for the second function, they're different functions. They have different signatures, but C will then be like, no, you can't do that. You can't have two different signatures for a function with the same name. Whereas Julia would be like, okay, cool. Those are two methods of one function. The function being multiply, the methods being multiply of integers and multiply of floats. So we're dispatching on the type of what the arguments are. That's kind of your idea of dispatch. You can choose which method to use based on which of the argument types being provided. So we say modal dispatch in contrast to single dispatch because a lot of languages, like kind of traditional object-oriented thing, will have single dispatch where you have a method of an object. So I said before that these were two methods of the multiply function. In a classic object-oriented language, you would have, this is the multiply method of float, this is the multiply method of integer. And you might like write that my integer dot multiply or my float dot multiply. Choosing which method to use based on only this like one argument. Like if I gave the second argument as, say, a float when the first one was an integer, it would still only depend on the integer argument. So I couldn't then go and define, say, multiply integer float that did something slightly different because it would only see the integer method. Whereas with multi-dispatch, I can depend on all the types of all my arguments.
So let's move on to contextual formatting, because I think that's the main thing we want to talk about today, isn't it? And the kind of project work that you did. So can you again introduce us to what you actually mean by contextual formatting?
It's a nice example of why multiple dispatch gives you kind of a power you need. When we talked about multiple dispatch, we said we're depending on types of both arguments. In any piece of code I can write with single dispatch, with no dispatch at all, I can depend on types of my arguments because I can just write an if statement. I can be like, if type of argument 1 is this, and type of argument 2 is this, and I can write out all the things. But for multiple dispatch, let's say later I wanted to introduce a new thing that I didn't know about when I wrote the first one. Maybe I'm in a whole other package reusing someone else's code. I can't then go and like add a statement to that big if clause to talk about a new type. Contextual formatting kind of helps illustrate this as a task. Let's imagine I'm generating some document like a LaTeX, something like LaTeX or like a paper, a report of some kind. And we can imagine that I have a number of different things I'd like to be able to display. I might want to display some text. I might want to display a number. I might want to display an equation. I could then write a method, it's like render for each of these, and it would put things on the screen. But then let's say I also would take into account the context. So imagine I could have, say, 3 contexts. I could have a diagram, just like a figure inside my document, or I could have the flowing content, like the main body text. Then I'd like to decide how I'm rendering them based not only what they are, because like a number needs to render different to like the rest of the text maybe, or definitely different to an equation, but also based on what context it appears in. So here I might say something like numbers in any context should be represented using a proportional figure. That's a proportional way to represent numbers. And then I might say that numbers inside a diagram actually should be represented in a sans serif proportional figure so that the diagram is more clear and easy to read. And so here I've needed to dispatch both on the fact that it's a number and I'm dispatching on the fact that it's in the context of a diagram. And then I might say flowing content should be in serif and inside diagram should be sans serif. So equations should be represented in standard color inside the prose. But inside a diagram, actually, we should put them inside a little box and color them bright blue to make them easy to read. And so here, like I've gone and I've made a bunch of rules, which like depends on both the context and it depends on what the thing being displayed is. If I then want to go and like extend this, say later on, I wanted to add a new thing, say a table. So in the context of a table, actually numbers should be displayed in what's called a tabular figure, where they're all kind of vertically lined up and so that you can like read them out of the table. So if I had just single dispatch, I wrote a bunch of ifs, I'd have to go back and open up some other code that I'd already written and add another clause for this table. I'd have to add it everywhere that it mattered. But with multiple dispatch, I'm just writing another method for it, and that can happen separately. I can even have an entirely separate package that just adds diagram support to this document. It applies to real Julia code, like all the internals for like how it does rendering and display of objects does something very similar to this. It uses like MIME types if I'm in Jupyter, Jupyter says, I support the following line types: Markdown, HTML, LaTeX. And then if I say jump, jump is a constrained optimization solver. So a jump object represents like a series of constraints. So I display it in my terminal, which says, I support plain text. It'll display as like basically a kind of ugly but readable enough representation of like what all your constraints were. So then display the same thing in Jupyter, and Jupyter said, I support LaTeX. Then it uses that context and says, actually, here's the LaTeX rendering of your system of constraints, and you'll get like a lovely LaTeX representation of your model.
Right. And how did you employ that actually in actual code in your projects? I mean, where do you make use of that? Could you give us an example of one of the projects that you might want to highlight to the listener?
So one of our projects is very much what I just described. We have basically a jump model to help represent what happens inside like a power system, like a power grid. And there's all kinds of things. Like you've got to make sure that you've got enough power to meet demand, but you're constrained because like a certain generator can only produce so much power. So we do have very much the system I described, where we have a way of rendering all the functions that we use to like describe our model. You can display them as functions, and they'll be like function thermal generator constraints. But then if you display them in the LaTeX supporting context, like in Jupyter or in the documentation, it'll be like thermal generator constraints. It'll display like a large equation telling you exactly what that function means. And yeah, we ended up doing this because, sure, we have this like system that like describes these things, but it's not that easy to like work out which bits are actually doing what when you've just got like a function with a name. So we want to like have a renderable documentation view of exactly what we are writing in the code.
Where would people actually be able to look at Julia code? Because I believe that you have a GitHub repository. Is that something that you could point people to? Where could they find you on GitHub?
Yeah, so I can be found on GitHub or most of the internet as Oxinabox, OXINABOX.
Okay.
Yeah, if you Google that, you'll end up with me.
If I were to go to this GitHub repo, what kind of project would you recommend that I look into to get up to speed with Julia language? Is there anything in particular you would like to point out, or do you think they're all equally useful?
That's a good question. It really does depend what your interests are. I have a project that's on my employer's GitHub called NamedDims. I think it's also linked from mine.
On the Invenia NamedDims, I think.
Yeah.
Okay. Mm-hmm.
So I think that project's kind of a good place to, it runs the gamut of kind of medium to advanced Julia code. Well, it's fairly carefully written in a number of places for performance, but it's doing a fairly typical operation, like standard matrix linear algebra routines. So it's not a bad place to start after you've done a tutorial or two.
I mean, what does this actually do? NamedDims, Julia.
There was a nice blog post went around by Sasha Rush, which was basically tensors considered harmful. And it was a criticism of how machine learning tend to just have these big n-dimensional arrays and then just have this comment saying, remember, dimension 1 is width, dimension 2 is height, dimension 3 is color channel, dimension 4 is time. And this blog post made the point, which was like, you just need to remember these. And if you get them wrong, your code doesn't work. So I was working on a project that was doing some machine learning. I got to it and I was like, oh no, now I need to divide average across time and take the mean across space, and that was dimension 2 and dimension 1. No, that's not the right answer. And I was like, I know I've screwed up a dimension somewhere. I'm not going to find this by looking at it. I should just implement a package so that making this kind of mistake is impossible. So I implemented this NamedDims package to find this bug. What it basically does is it goes through and says, let's say I'm going to multiply two matrices. And let's say they both have names. Then I need to check that the names of the dimensions, the second dimension of the first and the first dimension of the second, those need to agree. If they don't agree, throw an error, because it means I've lost track of dimensions somewhere and I've screwed something up. The output of this one should have the name from the first name from the first element, and the last name from the last array. And then we'll propagate that forward and we'll carry all those names through. So the nice thing about this was I just implemented this. All it does is knows about arrays and multiplication and like some other basic array operations. Then I went and I used it with the Flux package in Julia, which is a kind of deep learning package. And it doesn't know really anything at all about names. All it knows about is I do matrix multiplication, I apply sigmoid functions to things. But by using the named dimensions, I could just pass my named array straight through this whole Flux neural net, and out I got at the end, still had the dimensions I needed. Which, yeah, I think is like a really nice illustration of like how composable it was, is that I didn't have to touch Flux to get this support. Like the PyTorch equivalent, which is awesome and like amazing work, that must have taken them months because it looked really complicated. You have to go through and dig into like a lot of code to make sure everything is supporting everything. And then you can't go and use like that Flux, that PyTorch code with, I don't know, JAX or TensorFlow. They're kind of their own distinct little universes.
So, and this is where the strength of Julia comes in, that it makes that easier. Is that what you're saying?
Exactly, yeah.
So you mentioned matrix multiplication, because I think that's also a way. I mean, obviously, matrix multiplication plays an important role in machine learning. So how does multiple dispatch in Julia come into matrix multiplications?
Matrix multiplications are probably like the most canonical use of multiple dispatch. So if you've ever gone and read the source code or even the documentation for BLAS, you have a list of methods in BLAS. We have SGEMM, which is matrix multiply. Then you have SSYMM, symmetrics matrix multiply. Then you have like all of them until you get up to like ZHBMV, complex Hermian banded matrix vector multiply. What you have is actually, you have one function, you have matrix multiply. This is the idea. All of the other like letters, you're just encoding into your types, into your function name, basically your type system. You're encoding the fact that actually this is a symmetric matrix. This is a complex Hermian banded matrix. And so kind of the most natural way to do this would be if you have access to a type system multiple dispatch, and you can just write matrix multiply and just give it all these methods. If I want to go and like introduce some more matrices, like my NamedDims example I gave before, but also if I want to add some like matrix I got from scientific computing, say from the people doing differential equations, and they have banded matrices, which is you have bands of non-zero blocks on your diagonals and off diagonals. This one like kind of blew my mind was the banded block banded matrix, which is all of my blocks are themselves banded matrices and they exist on bands, which is like a really complicated and weird idea. If I was doing partial differential equations, turns out having this special type makes like solving a partial differential equation 4 times faster, which really adds up when this thing can take like hours to solve in the first place. It's reasonable, I think, for like someone who's working on these partial differential equations to implement this type. It's not reasonable for them to like implement BLAS. And that's, again, this is where kind of this like extensibility comes in. Just like I can write a named array package, they can write a block banded matrix package. Both will work not only with like normal matrices in Julia, but actually those will work with each other too.
I hope you enjoyed this mini-series on the Julia programming language. Next up, I'll be presenting a mini-series on software architecture, looking at how it might fit in with research software engineering, what enterprise architects do, and also talk to some solution architects from the Amazon Web Services. I hope you'll tune in, and with that, goodbye.